Okay, welcome to our third and hopefully final video on qualitative graphing. Here we have a graph, no numbers again, just the position is measured from the house to the road to the mailbox and back again. On this axis is time, but no numbers, just start and end. So what do we see? A slow, steady speed till we get to the road, then zero speed, then a high rate of speed, then zero again, then a high negative speed, and a low negative speed. Why? Because this is what's happening. Say over here by the flag is the front door. I'm just walking till I get to the road, stop with both ways, jog across the road real quick, get the mail, jog back across the road, and then walk the rest of the way back to my front door. Right? Nothing particularly complicated about that. And I know some of you have already seen this in class, but some of you missed it, and I want to make sure everybody gets this one. So now that we know that the velocity is just the slope of the position curve, we can actually make the entire velocity curve from just knowing what that looks like. In calculus, this is called taking the derivative, and if you think about the root word there, to derive, we are literally deriving a velocity curve from the position curve. And again, we don't need numbers to do it. We can just look at the shape of it and make another qualitative graph. Velocity is going to look like this. Zero will go in the middle. Up here is positive velocity, and down here is negative velocity. The further you go up, the more fast you are moving in the forward direction. And the further you go down, the more fast you are moving in the negative direction. So this is fast forwards and this is fast backwards, right? So let's think about that. I have a slow, steady speed at the beginning, so the line is going to go like this. And right here, it drops to zero. So down we go. And it stays at zero for a bit until we decide it's safe to cross the road, so zoop, we accelerate up to jogging speed and we stay there very briefly because it doesn't take very long to cross the road, and we go back to zero again. And then right here, we very briefly are negative jogging and then slowing down to negative walking. And that's the end of our graph. Notice they look nothing alike. There's no reason that they should. This graph is a graph of the slopes of that graph. And a graph, generally speaking, is not equal to its own slopes. There's only one exception that I know of. So that's what this is showing. This is that slope. This is that slope, which is zero. This here is that slope there, and so on. It gets better. We can also graph now the acceleration. That will also start at zero in the middle. Positive accelerations go up top, negative accelerations go down below. Positive accelerations might be extreme or strong, or they might be gentle or weak, right? If they're gentle, they're going to be down close to zero. Negative accelerations likewise can be strong, in which case they're going to be way down here, or they can be weak, in which case they're up close to zero again, but from the other side. And let's be clear, we know going in that there are 1, 2, 3, 4, 5 accelerations, and they're pretty brief. It doesn't take long to slow down from walking. It doesn't take long to speed back up to jogging. So mostly the acceleration is going to be zero, because most of these lines are straight, and accelerations only happen where that line bends. Further, we know that the acceleration should be negative, positive, negative, negative, and positive because of the happy-sad rule. Sad-shaped curves are negative, and happy-shaped curves are positive. So, the other thing to see is that the acceleration is actually the slopes of the velocity. This is, by definition, delta V over delta T is the acceleration, and changes in this curve, the rise and the run, would be delta V and delta T respectively. So let's just check that, shall we? This is supposed to be a negative acceleration. Is that a negative slope? Why, yes it is. This is supposed to be a positive acceleration, and that's a positive slope. So far so good. Those should both be negative. Are both those slopes downhill? Indeed they are. And finally, that's a happy face curve, so that should be positive, and that's an uphill slope. So let's graph this. All along here, that's flat. This is straight, no bends. So this should be 0 acceleration all along here, and then just a little blip of negative, and then a slightly bigger blip of positive, because it takes more effort to start jogging than it took to stop walking. Then we slow down from jogging, so that's a negative blip. And now we speed back up to jogging, but we're jogging backwards, so that requires negative acceleration as well. And finally, a little bit of positive acceleration to slow down from negative jogging to negative walking. And that's our whole graph. Easy peasy. So, I want to do one more just to cement the lesson. I am conscious of this taking time from your busy schedules, so I'm trying very hard to keep this graphing stuff short, but I want to make sure that it's also thorough. So here is our final test. I'm going to make another position curve like such, and the flag will be at the bottom, the filing cabinet will be at the top. This is our position, and the time will go from start to end, like always. And I'm going to demonstrate this. I'm going to go like this. Start. Ow. I think I hurt my knee. I'm not going to do it 3 times because you can just run the video back and watch it again. But it goes like this. I started, but I didn't start running right away. I just stood there like a dope. And then I gradually went faster, hit peak speed, and then slammed into the filing cabinet and stopped. And that's the end. So that's my graph. I'm giving you that. What I want you to do is make a velocity curve to demonstrate what's happening to the speed here, and then an acceleration curve to demonstrate what's happening to the acceleration. All right? And that's it.